Yeah, thank you for inviting me to give this presentation. Actually, I have to apologize to the organizer. In fact, my talk was scheduled for tomorrow. Some nice people, agreed to swap with me because I have a department meeting tomorrow, and I forgot to tell the organizer about the constraint. Today, I talk about a couple of research projects that I have done in the last couple of years. It is from a computer science point of view, applying to e-commerce systems. Okay, so to fit the theme of this conference, I put in big data challenges in recommendation systems. Okay, so this is the outline of my talk. Okay, first of all, I will give a background of recommendation system by means of examples. And then I will talk about a project that we collaborated with Alibaba in recommendation in their e-commerce network. And then I will talk about the utilization of site information. I would explain what it is, about site information and how we use what we know it as a heterogeneous information network to integrate site information. And then I would describe some experimental results. Okay, so everybody know about recommendation systems. Okay, Amazon make it well known to everybody. So a customer who bought this item also bought. Okay, so I just take this screenshot last night. So I click on a book on Java, and then Amazon would display this Hadoop book to me. Okay, so they are both books, but you can see that they are of different contents. Okay, Java and Hadoop. In principle, Hadoop is not a programming language. And then you go further, and Amazon would make another recommendation, or another kind of recommendation that is, customer who search for something ultimately bought something else. Okay, so I type in desktop computer, and that is what Amazon gave me. Okay, so actually, this is not advertisement. This is actually, I guess, from their statistics, collected from the users. So you can see that HP desktop is really popular. It's quite cheap, and so on. And then you also have yet another kind of recommendation. Okay, so these are kind of new. I didn't encounter them maybe just back a few years ago. So this is inspired by your browsing history. So you browse the website, and obviously I look at books and related to computer science, and then you will recommend some a computer accessory to me. Okay. So I think this just highlight the importance of recommendation systems, and there are a lot of articles describing how much this e-commerce website depend on recommendations to make money. Okay, so this example illustrates that recommendations are based on user behavior, because it really look at what people which pages people access it, and whether they bought the item or not. So it is much more than a content similarity. Okay, because many small items do not have content anyway. Okay, and then we will look at this a project we collaborated with Alibaba just last year. So I think the big problem with Alibaba, of course, is also their good problems. Okay, that is they're huge. They have 1 billion users, and there are 2 billion items online. Okay, for people to purchase. So you can see that there are a lot of possible relationship between users and items. Okay, so with this huge amount of items and number of users, you get a lot of sparsity. Okay, so we have some data later on in the experiment. Okay, so you can imagine that most users, would be buying a fraction of the items. Even though they may be buying like hundreds or even thousands, but compared to billions of items in the warehouse, that is just a small part. Okay, they also have a cold start problem because every hour, I think it is hard for me to believe, but this is the number they gave us. That is, every hour there are millions of items uploaded to the e-commerce website. So the challenge is that how do we maintain good quality recommendation in face of this huge number of data, huge amount of data. Okay, so we basically target at Taobao, which is the most popular e-shopping website in China. And a lot of users make use of this Taobao mobile app to access to the website. So here we took several screenshots from the Taobao mobile apps. So one very important thing is that they actually personalize the homepage for everybody. So it's not that everybody look at the same page. So the parts that is highlighted with these boxes are actually personalized. Okay, there are 3 screens. Depending on the user's access history, the user will see different things. Okay, and this is an important problem because 40% of the total recommendation traffic from the entire Alibaba website came from this homepage. Okay, they look at this homepage, they like what they see, they will click on it. Okay, so that would mean a lot of businesses for them. And then because of this huge scale of data, okay, so the design of the recommendation system has to cater for this scale. Okay, so essentially, the recommendation is divided into 2 parts. One is the matching part. Okay, so in the matching part, there is no users in it yet. Okay, that is the individual users. So we of course have a community. All of the users access data collected over years of operations. Okay, and every user have a sequence of accesses. Okay, so this is time sequences. Okay, so we have billions of them, and everyone maybe have thousands and maybe tens of thousands of accessed items. And then we build a similarity matrix. That means we measure the similarity between the items and build the matrix. So this is called the matching part. And then on the right-hand side, when the user visit the website from here, okay, so essentially the trail of the access will be recorded in the user history. And then this, according to what the user access, you would retrieve a number of similar items for what we have compiled here. Okay, and this item is could be hundreds or thousands in terms of similarity. And then they further use a personalized ranking techniques to rank these items. Maybe at the end you would just display 10 items to the users. Okay. Now in this part we will just talk about the matching part. Okay. This is really huge, right? Because this is the most challenging part in terms of size. So here we look at an overview of the methods that we use. Okay, so on the left-hand side, so we have all of the users' accesses. So the first step is to clean out the data, and then to segment the accesses into sessions. Okay, because people may just spend 1 hour in buying something and then go to sleep. Next day they will buy something else. So they will be divided into some sessions, and then these sessions will be combined together across all users, and then we create this what we call the item graph. Okay, this is the second part. So this graph is huge, and it basically aggregates all of the users' behavior in one graph. And then while the graph is huge, we need to deal with we cannot do any sophisticated graph search in real time. So we use a random walk to sample and learn the structure of the graph. Okay, so the random walk would produce a sequence of paths, and then from the path we use graph embedding to generate the embedding for all of the nodes in the item graph. So here we go into a little bit of the detail. Cleaning, I think segmentation is simple, but I think it is interesting to look at the cleansing part because there's so many users accessing the website. So we have to remove some noise or something that is not concrete enough. For example, all transactions source state would be discarded. If you stay on the website on a particular item for less than 1 second, then it means that you are not interested really in that item. We also remove all users that is hyperactive. Okay, that is they generate a lot of purchases and generate a lot of clicks over a short period of time. Okay, for one thing, they may be robots. For other things, they're not actually representative of the general individual users. Okay, and then finally, we remove all items which has been updated so much that actually the item that you're looking at is quite different from the item that was on the page a few months ago. Okay, so the interesting thing is that the vendors who are selling items on the website tend to use the same page to sell different items. Okay, and the reason is easy to understand because people the users go to the website. They want to understand how reliable how trustworthy that shop is. Okay, what is the quality of the items? Okay, there are a lot of doubts because you are buying online. Okay, so people tend to look at the how long the shop has been around, how long the shop has been selling that product, and how many items has been sold. Okay, so the vendor would make use of this psychology and then just try to keep use the same page, because even if you have a new items, okay, there will be years of purchase record, presumably with good comments and so on. Okay, so this is again not really representative of the typical items. So we remove all of them, and then from this sessioned or partitioned access log, we create this item graph. So essentially, when you see two consecutive items in here, DA, then we would add an edge in here. Okay, and the number of appearances of DA would be the weight of that edge. Okay, so at the end we created this item graph. So this item graph contains millions of nodes. So we do a random walk on this graph and generate the paths. Okay, so this is a standard random walk. Essentially, when you're at a certain point, you will transit to the neighbors, according to the weight of the links. Okay, and actually, and then so this is one path. Okay, AB, EB, which is corresponding to the last path, and then we just generate a lot of them. Okay, and finally, from this path, we generate the graph embedding. Okay, graph embedding is essentially to look at every node, and we want to create to learn a low dimensional representation of that node. Okay, so the criteria is to minimize, is to maximize the co-occurrence probability of two nodes in a certain windows. Okay, for example, A and E. So I highlight the A's here, and then you can see that A and B co-occur a lot, and therefore their embedding should be learned in such a way that a high similarity between the embedding would indicate a high co-occurrence probability of the two nodes. Okay. Now, This item graph is just recording the user accesses. Okay, so we address make use of another signal that is called site information in general in the recommendation system community. Now, the problem with just looking into the item graph is that it does not solve the cold start problem, right? Because if you have a new item, the item has not been accessed, and then it would not be put into the item graph. Okay, and since there are so many new items, every day, so that actually would represent a lot of businesses, okay, for Alibaba. So we look at site information. So site information is essentially information besides user item interaction. User item interactions are like purchase and access to particular pages. So on the user side, we can have site information like user attributes, okay, social connections, and so on. From the item side, you have these item attributes as well. So you may have product categories, brands, shops, and so on. And then there are additional user item interaction, okay, besides purchase and page views. Okay, that is actually like on Amazon, some people would write reviews for a particular product and then give rating. Okay, so these are also important information for inferring whether an item is a good recommendation for particular users. So in the Alibaba project, basically Alibaba claims that they use hundreds of site information. But in our experiment, we took on some 20 plus site information. So this is essentially product information, the shops, and so on. So this site information give us additional signals for evaluating the similarity between the items. For example, if we have two dresses that is coming from the same category and from the same shop, then we will look at them as more similar compared to dresses coming from different categories and different shops. Okay. So the general principle is that if you have items with similar site information, then they should be put closer in the embedding space. So you can either use embedding and then just use learning to find out to learn the embeddings, the item embeddings, by considering the user item interaction as well as the site information together. The other approach is to use a more semantic approach. That is actually to understand the semantics of the applications and then use that semantics to infer relevancy. Okay, so this is called heterogeneous information networks. That is actually a separate project that we have done. Okay, that is not with Alibaba. So what does it mean by heterogeneous information network? So it is essentially a graph connecting different type of information. So it is the important thing is that it is heterogeneous. Okay, so I think unlike a lot of problems which deal with a homogeneous graph, so you can see that there are users, there's items. In this case, these are actually restaurants, okay, selling different items, and then user write reviews on different aspects of the restaurant, and then the restaurant has locations and so on. Okay, so this could be a very complicated graph, and we can represent them as a schema, okay, including some relatively static information as well as information about user activities. So notice that this is actually the user item interaction, and this is actually they are not the user is not actually buying anything, but just write review on that restaurant. Okay, so with this graph, we can infer the similarity or the relatedness of two heterogeneous objects. For example, the first one. So sorry. Okay, so I just highlight some example. So in this case, we have a user one who is a friend of user 2, and user 2 check into a particular restaurant, okay? And then we can actually represent this information with a more complex schema. So user 1 connect to user 2, and user 2 connect to B2. So with this piece of information, we can actually infer that by social relationship, we can also infer that U1 is likely interested in B2 as well. Okay, so this is basically a social recommendation. And then the second path, we can look at, even though we are still looking at user 1 with a particular restaurant, but the path we take is different. So we are following the check-in path. It means that both U1 and U2 visited the same restaurant, but U2 visited another restaurant. So we can also infer that, well, since U1 and U2 maybe like or dislike a particular restaurant, so they would likewise, like or dislike the other restaurant. So we can also express this relationship with a path like that. So we can go in a more complicated one, and then looking at users who write a review on the same restaurant, and presumably with the same type of ratings, are also more related to each other. So overall, we look at a simple graph like that. You can or we had generated 9 such relationships. Okay. By the way, this is actually I forgot to mention that this is actually a schema extracted from the Yelp.com. Okay, which is a restaurant or business rating website. Okay, so essentially, this is a compact representation of the hint that is a schema. So we look at different paths and then generate different relationships. Okay, so the first one is a user-user inform relationship. That is the social relationship that we looked at earlier. And then we come all the way. I will not go through them, each one of them, but this one is really a complex one, which is actually a graph connecting a particular user to a particular business, because they write a review on yet another business. In this case, this is B1. So the user actually write a review on a particular restaurant, mentioning a particular aspect, like the price. Okay. And then if you have 2 similar reviews written by 2 similar users, then these 2 users would be similar, and therefore we can also infer that even though U1 hasn't visited B2, so we can infer that U1 may be interested in B2 as well. So we use this kind of semantics to infer, rather than just using purely machine learning. Okay. So we look at some experiment. I highlighted the data set that we use in Taobao and compare it with Amazon. Amazon is publicly available. Okay, you can download it on the website. On Taobao, I don't think they make the data set available so far. So you can see that the data set from Taobao is much bigger than the one that is typically used in other research with more than 2 million, 2.5 million nodes and 44 million edges. And in both cases, the sparsity, the density is very low. Okay, 0. Something like 1%. And we evaluate the link prediction. That means that we hide some links, and then we try to predict them. So I will not go into this. This is quite standard experiment setup. So we compare the basic item graph embedding methods with 2 existing graph embedding methods that were proposed earlier, and so on. So I will not go through this detail, but just to note that I think the interesting to note that of course we have a better performance compared to the basic one, or compared to the existing baseline. But you can see that for Taobao, actually the performance is higher, much higher than the Amazon. Okay, that means that having more data is actually a benefit in terms of the prediction accuracy. Okay, as long as we can manage the time complexity. Okay, and the second experiment, so the first one was done offline. So we just collected the data and do the offline analysis. The next experiment we did was actually we did an A/B test, okay, on the real Alibaba website. So that was done in November last year. So if you know, November is a big day for all of the e-commerce website in China. That is because they have this Double 11, okay, big sale, okay, every year. Okay. So we deployed the algorithm for 7 days, okay, in that month, and then compare it with a previous click-through rate. So CTR is the click-through rate. So we compare a different method. So this is the method that Taobao has been using, okay, before. Okay, my understanding is that they have actually deployed the item graph method in their system, and these are all open information. You can find them on the web. Okay, so this is the basic graph embedding without side information. Okay, the first one that I described. The second one is that we actually use the side information but without any weighting. So every piece of side information is considered equal weight. And then the last one is the side information with weighted. So we use an ensemble method to learn the weighting. So the click-through rate being higher the better. So we see the green one, that is the weighted one. Okay. So the click-through rate is like 0.0 something. Okay, but comparing to the overall volume, that happens every day in Alibaba. Actually, a small percentage increase mean a lot to them in terms of revenue. And then we also get into some in-depth study of the result. Okay, so we project the item embedding into 3D. So actually, I think it is not clearly shown here. So we have this 3 dimension. I think we should have used 2 dimensions to make it even clearer. So there are 7 item categories. So we present it with different color here. So you can see that by and large, items with the same categories are clustered together in this space. Okay, and then we point out one interesting observation. We just highlight 3 product categories, and they are badminton shoes, table tennis shoes, and then football shoes. 3 kinds of shoes. Okay, and then we projected it on this 3-dimensional space. So the green one is football. The red one is badminton, and this yellow-orange one is table tennis. Okay, so they're in 3 different groups, and you can see that these 2 groups, badminton shoes and table tennis shoes, are much closer to each other compared to their distance, from the football shoes. Okay, even though they are all shoes. Okay, so the interesting observation, if you can imagine that is in China, maybe in general, people who like playing badminton, they would also play table tennis. Okay, and vice versa. Okay, because at least both of them like play in a similar way, and they are both indoor. Okay, football is kind of something very much more exotic, compared to table tennis, right? So this is a interesting observation. So when people look at badminton shoes, you may as well present table tennis shoes to them, okay, rather than football shoes. And how do we handle what is the performance of cold start problem? So cold start problem means that you have an item that is brand new, okay, and then we input it to the system, and we look at the recommendation. Okay, so this is at least looking at the 4 items, they are quite proper, given the original cold start problem. And here are the categories, upon which we use to infer these suggestions or recommendations. Okay, and then we look at the weighting, okay, of several sample items, and then the item part is actually the axis, okay, the user item axis. The darker means that the weight that we learn from the training data is higher. Okay, so obviously the actual axis is most important, but then if you look at the size information, okay, this is the level 1 categories, level 2 categories, and soft brands and so on. And this dark color also is a clear indication that across quite uniformly all of the item, soft is a very important property, okay, or size information in making recommendations. So it is a lot better to recommend items from the same shop. Okay, and that will lead has a better chance for the user to be interested in that item. Okay, so according to our collaborators' experience in Alibaba, so they kind of use Alibaba a lot, right? So so the explanation is that actually a lot of shops offer discount for people who buy a lot from the same shops. Okay, for example, they offer you free delivery if you buy more than like $20 and so on. Okay, and this is the general architecture, and so this also highlights some the size of the experiment. This is for offline, 600 billion entries in 3 months, 100 billion sequences. We actually use their machines, 100 server with a GPU. Running it for 6 hours, and then that's it. Okay, we can generate the graph embedding. So one thing that we did not cover, this is actually done by Alibaba themselves. That is on the ranking part. Okay, so we are not working on this. Okay, so the other one is the evaluation, a deeper evaluation of the importance of size information. Okay, so I think I will just go through it. This is the statistics of the 2 data sets, the Yelp.com and Amazon.com. And without going into the detail, I just want to highlight something that is size information actually from this experiment illustrate a significant improvement. So you can see that in our previous experiment, as well as in many experimental results reported in the community, so you are talking about like a few percentage point increase or improvement, and with a large number of size information available, you can see that the improvement is actually quite significant compared to the fact that you are just using the user item interaction matrix. So from the 9 relationship that we extracted from the heterogeneous information graph, and obviously we combine both of them and then learn the weight and so on. So this gives you the smaller error. And then the other one, we also kind of observe that if you trace M2, M3, and the better performance one, M2, M3, M8, and M9, so they're all based on this kind of pattern. Okay, what does that mean? Okay, it means that if you can establish a relationship between 2 users, okay, then the interest of one particular user has a big impact on the other users. So these are actually users interaction. Okay, for example, in a social network, if you have 2 users who happen to be friends, if you have 2 users who happen to buy the same item, okay, that means that they're very close together, and therefore an item purchased from one of them would very likely be liked by the other users. Okay. On the other hand, item base is less effective. Okay. I think this is kind of discovered for a long time in the community. That is, if you have 2 items that are similar, for example, located in the same city, or belonging to the same type of restaurant, that doesn't mean that the user would like all of them. Okay, so user similarity is much more important than business similarity. So here is some a conclusion. So recommendation system, I think no need to emphasize, is very important for these big e-commerce companies, Alibaba, Amazon, Netflix, and so on. So community behavior is very important on the one hand. So and site information is also very important as supported by our experiment. And we should our expectation is that site information will become more important and moving into like a central information, maybe just as important as the interaction matrix by itself. The idea here is that website is growing bigger and bigger, offering more and more functionalities. Okay, so they can actually capture a lot of information about the users and how they use the products. And then our experiment with Alibaba also illustrates that machine learning technique is very effective as well as efficient for billion scale data. Okay, I imagine that if it's good for Alibaba, it's probably good for a lot of other companies. Okay, so finally, this talk is actually a summary of the work that we have done. So one was published in last year. KDD, I don't know, it doesn't show the year, but 23rd, and this is 24. So this one is 2017, and this is just published a couple of months ago. And this one is a study of social information in collaborative filtering. So if you want to have more information, you can look at this. Okay. Any questions?